Hey, what's up, guys? This is Akshay from AS Learning, and today in this video, we'll be seeing about clustering in brief, that is, theory about what clustering is. Then later, we'll be seeing its practical implementation and also evaluating how to come up with the proper value for k uh, in two or three methods. Okay, and we'll also go into much detail on how exactly clustering is, and in short, understanding what's the core crux of clustering and what's the main idea behind it. Okay, so clustering comes into unsupervised segment of machine learning. So generally, when you don't have labeled datas, so to solve those kind of problems and see what can we do from that data. Okay, so whenever you have labels associated with your data, so generally it is treated as a supervised learning problem, and if it does not has a label, then it falls in the category of unsupervised learning. Okay, and from that data, then either what we can do is we can create our own labels. Okay, or we can add labels to it. Okay, or from that unlabeled data we can go for some insights. Okay, we can group that data into different segments and get that insight from that data. Okay, so whenever your objective is to group a certain data into certain categories or segments, clustering is one of the weapon in machine learning which you can use. Okay, so let's just have a brief understanding for those audience who don't know clustering at all, or maybe just need a quick revision on what exactly it is. Okay, so it's a technique used in machine learning and data mining to group similar objects and data points together based on their characteristics or pattern. Okay, so on the basis of their characteristics or pattern, they would be grouped into one segment or one group. I'll say, let's say if there were class of students, so we can say that class of student itself is a clustering done. Okay, we have so many classes, class 1, class 2, up till class 10th. So how is that clustering done? On the basis of their age. Okay, when they did their admission into school. Okay, so if let's say someone else comes and he tells me that okay, my age is this, and I have and this is my educational qualification. Let's say he has cleared up till class 4 or class 5 into another school. On the basis of those characteristics, we would decide that, okay, seeing your achievements and your age, I feel that class 6 or maybe class 7 is best fit for you. Okay, so it's just an one example of grouping that entire students data into classes. Similar way, you will see clustering everywhere, into nature, into your homes, into your daily activities, everywhere. Okay, it's a very loosely used thing, and yes, with the help of machine learning we can include it into our data set. Okay, so it's an unsupervised learning method, meaning it does not require any labeled data or predefined categories. So I have already discussed this point, I won't repeat it. Okay, the goal of clustering is to identify inherent structures or relationship within the data and group similar items together while keeping dissimilar items separate. Okay, so the two clusters should be unique, that's the goal. But is it a mandatory condition? No. Clusters in clustering can overlap also. Okay, but to have good uh, clusters, they should be unique and they should be separated from each other. There, um, the distance between these two clusters, that is the intercluster distance, should be as high as possible. Okay, then clustering algorithms accomplish this by quantifying the similarity or distance between data points and creating clusters based on those similarities. uh, creating clusters on the basis of distances, leveraging distances like Manhattan distance, Euclidean distance. Okay, so that is one of the way of creating clusters. There are various ways, but this is the most commonly used way, and it is also very effective. Okay, you can also take into consideration direction aspects into vector spaces for creating clusters. You can take into consideration the different encodings, whether it's an image encoding, word encoding, whatever encoding to create clusters. You can take distance is most common way. If you go to more advanced ways and all, then vector spaces or image encoding spaces. So these things are something which can also be taken into consideration for creating clusters. There are various clustering algorithms. Okay, so now you have to group them into one unique groups. Okay, so there are many algorithms. Okay, the most popular ones are k-means, hierarchical, db-scan, and Gaussian mixture models. Okay, so in this tutorial, in this video, we'll be covering just k-means. Okay, and in the coming tutorials I'll be covering db-scan, agglomerative, it's like hierarchical clustering, and finally Gaussian mixture models also. Okay, so this video, the scope is limited to k-means. Okay, and clustering finds application in various fields such as data analysis, image segmentation, customer segmentation, document clustering, anomaly detection, and many more. Okay, these are very common applications, but very effective applications in almost every field. Okay, uh, this was just some amount of quick revision for you what clustering is. Now let's start with the practical part. Okay, so I'll parallelly be running the cells also. So here I'm importing my libraries. Matplotlib.pyplot is for data visualization. Okay, then I will be leveraging sklearn's dataset library for creating my synthetic data. Okay, pandas is for data pre-processing, and numpy is basically used as a inner data structure uh, for implementing the k-means algorithm and the other algorithms of machine learning. Okay, we use numpy over the uh, generally used Python data structures like dictionary list because of its computational beneficiation it brings on the table. Okay, speed gets very high. NumPy is basically the library which is used when you try to implement linear algebra. Okay, so matrix multiplication and all those things are very easy when you treat your data as an n-dimensional array. Okay, then below this warning is just to avoid the red warnings which come. Okay, then here I'm creating my synthetic data, make blobs. The number of sample I've kept is 500 for simplicity. I'm keeping the center as 4. That is, there will be 4 distinct unique clusters. Okay. Number of features are 2. Okay. That is, we have x1 and x2 as 2 features. And the random state I've kept is 14. Okay, so what random state is? So in short, if I tell you, if you want to reproduce the same results in any another notebook, because it's a synthetic data, so if you will use the same random number 14, the same results will get generated. Okay, that's the major use for random data. Okay, xy, I guess I'll delete these cells. Okay, so if I want to show you the data, I'll just quickly show you data x. So these are my 2 features. Okay, which have been created by make blobs. So can anyone give a thought why in like what distribution will be covered in this synthetic data? Okay, like y is only the data roughly between -11 to +10. Okay, so if anyone has an answer to this question, just ping it down in the comments. Okay, I'll say you explore on the distribution front also, how this synthetic data is generated and why we are seeing these values only. And if, let's say, if you want to have some another totally different values, so how will you approach it? Okay, then I'll show you the, okay, accidentally I clicked on text. Data y. So these are my centers. Okay, so as you can see here, it is 0 1 2 3, so that means we have 4 clusters. Okay, so this is my synthetic data which I've created. It's a label data. Okay, this is a label data. Now what we'll be doing is taking this data underscore x, I'll be fitting k-means, and I will be seeing that without using the labels, how k-means is coming handy to give me the exactly 4 clusters which are there present in the data. Okay, so these were some earlier iterations when I did it with 3 clusters. So now we should be able to see 4. So as you can see, we have very 4 unique clusters in the data. Okay, now here I'm loading my k-means. Okay, I'm loading it from sklearn's cluster package. Okay, WCSS is within cluster sum of squares. Okay, and what I'm doing here is I'm iterating on a range of 1 to 11. This is a randomly picked number. Okay, I'm initializing it with k-means plus plus. I'm fitting it and then I'm appending the inertia scores to my list of WCSS. Lots of terms, lots of things happening here. We'll see it step by step. So the first line is I imported k-means, okay, from my package sklearn.cluster. Okay, simple. So I've been importing my k-means class, which contains all the functions needed to help me apply k-means to my data. Okay, now what is WCSS? WCSS is within cluster sum of squares. Now what is this? This is my cluster. Okay, so I will be calculating the inertia of this cluster. Now inertia goes in similar lines with WCSS. So I will be calculating the sum of the squares, okay, from the centroid to every point. Okay, so there will be a centroid picked, and from that centroid to every point, the distances and its sum would be calculated and stored. And in this way, the entire inertia of that cluster will be calculated. Okay, so what is within cluster sum of squares? So it is nothing but from the centroid to each respective point, I will be calculating the distance. I will be squaring it up, and then I will be calculating its sum. Okay, so it will give me an idea of the inertia in the cluster. Okay, now we saw what is WCSS. Okay, now we will be seeing what is this initialization parameter. So we are given two options by sklearn's k-means package. One is random and one is k-means plus plus. Okay, now what happens in randoms is out of these points, randomly the centroids are picked. Now they can be here, so all the 4 can lie here. Okay, or maybe 2 can be here, 2 can be here. Okay, so it is random picking of the centroids. This leads to a lot of time complexity being involved. Computation will be high because we know that if the centroids are picked here, it will take some amount of iterative steps to come up with a centroid in this cluster. Okay, Now this is where the k-means plus plus come into advantage. What it does, it takes into consideration the inertia and it sees its empirical distribution, and on the basis of that the centroids are picked. So very smartly the centroids will be picked year and year only. In this, they may not be in the center exact, okay, but somewhere here only. Maybe this point can be the pick centroid, this can be one, this can be one, and this can be one. It will take into consideration the inertia, okay. And in this way what will happen is your iterative time will go down, okay, the time complexity will go down, okay. So this is the difference between random and k-means plus plus, okay. Now after that what you are doing is you are selecting your you are iterating on a range of 1 to 11. You are giving each number an option to be the number of clusters. You are fitting the k-means and then you are appending whatever the inertia is to my list of WCSS, okay. Now this is my WCSS, okay. Now what I'll do is I'll be plotting this WCSS and the number of clusters which I selected here, okay. So let me run it again. Okay, it is telling me X is not defined. So it is data X, okay. Now this is my WCSS, that is the inertia list. Now I will be plotting this with the help of I will be plotting this on the y-axis, and on the x-axis there will be number of clusters. Now here we can see that we have three probable options to be selected as the number of clusters. One is you can select 4, okay. You can select 3 or you can select 2, okay. By seeing this graph, I would have been confused between 3 and 4, okay. It is very somewhat tough to decide whether I should go with 3 or whether I should go with 4 here, okay, because this method is nothing but the elbow method. Here we are seeing that and on which point exactly there is a sharp change in the WCSS, and we can call it as the elbow point. Now here you can call 2, 3 and 4. All these 3 points can be considered my elbow point, and you can consider maybe 3 and 4 very close, okay. Here also if we see, maybe the 3 and 4 are coming very similar because these two clusters are somewhat being intermixed. Okay, so these two can be considered as one cluster and these two can be considered as my separate two unique clusters. Okay, so how to get more clarity on it and what to go ahead, we will be seeing it later on. Okay, now let me do one thing is now I'll be running it again. Now here I've kept it number of clusters 3. Let me make it 4. Okay. Here I'm getting the y label and why is this coming as 3? It should come as 4. Now because I wanted to have 4 clusters here, so I'm just showing you in visualization how those 4 clusters would come up. Okay, and if we go ahead with the 3 clusters elbow point, then this is how those 3 clusters would look. Okay, now because we can visualize the data, it becomes very easy for us to tell, okay, our 4 clusters is better than 3. Okay, so what we did was we visualized the data, we had the option of 3 and 4, and seeing that if I would have been in this place, maybe I would have gone with 4 clusters, but not every time you would have that option to visualize the data. Now this data is a two feature data, so it becomes easy to visualize it on a scatter plot. Let's say it is multi-dimensional data. Okay, now visualization, now doing its a visualization on a multi-dimensional data is not possible. You cannot see every dimension. Even if you do some kind of a transformation and by retaining its variance, you brought it into two-dimensional thing and you do it. I think it's not a good way, because there is a lot of loss of the original characteristics when you do such kind of a transformation. Okay, now how to decide that? Now here it became very easy for me because I had the I'll say extra advantage of visualizing my two features. Hence I could say that okay, fine, between 3 and 4, 4 is a better option for me. Okay, but how to do when you cannot visualize it, when it's a multi feature data set? It will become tough. If you try to bring those data set back into two dimensions and then you try to do it, it's not a good way and your results can get screwed. Okay, now what we can do is here we can try some other methods also. Okay, now we just saw the elbow method with the help of within cluster sum of square. We can try some other methods and see that where is the inclination, whether it is towards 3 or whether it is towards 4. Okay, so one another package which you can use and it will come handy is K-Need. Okay, so this package has its own documentation also. So here I'll be importing knee locator. Okay, so this also takes into consideration the elbow factor only. Okay, so instead of elbow, it is telling it is using the term knee. Okay, so as per knee locator, 3 is the right option for you. Okay, so it is telling us that as per knee locator, 3 is the right option in 3 and 4. I passed it a range from 1 to 11 to come up with one number. So as per him, 3 is the right option for us. Okay, now we'll see how this knee locator exactly works. Okay, now here you can see that I am passing the WCSS, the inertia list. Okay, the curve here I've kept is convex and the direction is decreasing. So I'll tell you what this convex and decreasing thing is. So here you can see that the graph is a decreasing graph. It's not an increasing graph. Hence the direction is decreasing and it's a convex curve. If this curve would have been in this fashion, it would have been a concave curve, or in this fashion, it would have been a concave curve. It's a convex curve and the direction is decreasing. And as per knee locator, the number of clusters it is telling me is 3. Okay. Let me try one more method. Now this method is called as Silhouette score. Okay. Before explaining the practical aspects of Silhouette score, let me explain you how this Silhouette score works. Okay. So see, Silhouette score is one another way of coming up with the optimum K value for clustering. What it does is it takes into consideration the intercluster distances and the intra-cluster distances. Okay, and it calculates the Silhouette coefficient. Okay, so there are two things which are taken into consideration. One is cohesion and the other one is separation. So cohesion means how the clusters are compacted and how they are. So are they loosely bounded clusters or they are compact clusters? That is defined by cohesion. That is defined by intra-cluster distance. That is defined by A in my formula of Silhouette coefficient. What is A? Is the average distance between the data point and the other points within the same clusters. Okay, so what it does is with every data point in that cluster, it will be calculating its A, and then it with the overall A of the entire cluster, it will be taking the average. And we would be considering that average A value for that entire cluster. Similarly, we would be calculating the B value also. Now, what is B value? It's a measure of separation. It's a measure of intercluster distance. Okay. What it does is, now let's say there was a point A1. Okay. Now in cohesion, that is intracluster distance, that from that point A1, I will be calculating the distance from, let's say, A2 and A3. Okay, there are, let's say, 3 points in that cluster. Okay, I calculate the distance between A2 and A3, and I'll be taking the average score. So that is my average intra-cluster distance for point A. Similarly, I'll be doing it for A2 and A3, and then I'll be taking the overall average. Okay. What I'll be doing in B is the point A1. I'll be calculating the distance from point A1 to B1, B2, and B3. Let's say there is another cluster second. Okay, and that cluster, there are points B1, B2, and B3. Now from A1, I'll be calculating the distance from A1 to B1, A1 to B2, A1 to B3, and I'll be taking the average of it. Okay, so that will be my average intercluster distance for point A1. In this similar way, I'll be repeating this activity for every point, that is A1, A2, A3. Okay, and in this way, I'll be having an average score of A1, of A and B for that cluster. And in this way, I'll be calculating the Silhouette coefficient score, that is B minus A upon max of AB for that cluster. Okay, somewhat confusing. So I'll repeat it. Okay, first I'll make it simple. Silhouette coefficient is B minus A max AB. So what is A? So A is the intra-cluster distance. Okay, let's term it as the average intra-cluster distance for that entire cluster A. Okay, I'll just change the name of clusters. Maybe I'll just make it C and D. Okay, so for cluster C, I have my average intra-cluster distance as A and my average intercluster distance as B, and hence I'm getting the Silhouette score of B minus A upon max of AB. Okay, so this is my Silhouette score for cluster C. Okay, and how is that average score being calculated? That average score is being calculated when I'm doing this activity of intercluster and intracluster for each point in that cluster C and then averaging it out. Okay, if it's still confusing, okay, maybe I'll make one separate video on how Silhouette coefficients are added. How are they exactly calculated? Okay, if you find that this explanation was confusing, just ping down in the comments and maybe I'll make a separate video also. Okay, now with whatever score is coming from Silhouette coefficient, now how to analyze that score? Okay, so if the score is close to plus A, so it suggests that the data point is well matched and it is assigned to the right cluster and it is far away from the neighboring clusters. Okay, this Silhouette score is ranges from -1 to 1. Whenever it's -1, it's an indication that the point is not in the right cluster. Okay, it has not been assigned to the right cluster. Okay, and when it is close to 1, so that's an indication that it has been assigned to right cluster. Okay, and if it's 0, that means that it is between those two clusters, somewhere between. That is where my point is. Okay, similar to Silhouette score, we have some other scores also, like Kalansi, Kerbach's index, and Davis-Billings index. Okay, so this comes into some amount of advanced topics. Okay, so we saw what is Silhouette score. Now let's take handy and calculate in our case what does Silhouette score tells me, whether I should go with 3 or whether I should go with 2. XXX. So these are my Silhouette scores. And let's see whether Silhouette score tells me. Now as per Silhouette score, there's a tough competition between 3 and 4. Okay. But as per him, 4 is a better pick. Okay. So what I saw was Knead told me that 3 is the right pick. Silhouette score told me that 4 is the right pick. Seeing the elbow method, I was confused between 3 and 4. Okay. So we can pick both of them. Seeing the visualization, it told me that 4 is a better pick. Okay. But now seeing all these scores, now what to decide, right? Which should I trust and which should I not trust? The most important thing which will come handy in deciding whether we should pick 3 or 4 is your domain knowledge. Have a talk with the business analyst or the domain expert of the data and tell him that if we go with 3, what will be its consequences, and if we go with 4, what will be its consequences. Have a domain guy's perspective on it and then take the final call, whether it should be 3 or whether it should be 4. Okay. So in short, what we saw in this video was we saw some brief about what clustering is. Then we took a synthetic data, we fitted k-means. Then we saw 3 different techniques in which we came up with the optimum values of k. One is elbow method, the another one is Knead package, and last one is Silhouette score. This Silhouette score, I'll say, needed dedicated video and some visualizations also. Okay, but I hope I was able to cover what exactly is Silhouette score and what does it mean. Okay, so that's it, guys. If you like this video, if you find it helpful, just give it a comment, share it with your friends, and stay tuned to AIS for more such amazing tech stuff. Take care. Peace out.